Hey guys, Mr. Thomaswick here. Since we aren't going to be in school today due to weather, we wanted to make sure you weren't missing out on your daily dose of math. So what we have done is we have filmed a series of short videos that are going to go over some of the proofs that we're going to be talking about in class. What you guys are going to need to do is to go to your theorem section of your notebook that we started in class the other day with our vertical angle congruence proof. And you're going to add each of these proofs into that notebook section. We're going to have 5 different videos. Each one is going to be on a different proof, and you'll need to make sure that you put those into your notebook. You'll want to copy down the given information that you see on our screen, so probably the first thing you'll want to do is go ahead and pause the video, draw your little shapes and diagrams that we have, and write down the given information. And then once you have that down, go ahead and resume the video, and we'll go over the rest of the proof with you guys. Alright, let's go ahead and jump in. Alright, so the first proof that we're going to start off with in this series is going to be the alternate interior angle theorem. And that theorem states that if two parallel lines are cut by a transversal, then alternate interior angles are congruent. So before we actually get started with this proof, we need to just review some background information. This should be information that you have recognized from middle school, but we just want to make sure it's fresh on your brain before we go into this proof. The first thing is what alternate interior angles are. It's going to be hard to prove this theorem if we don't understand what alternate interior angles are. Alternate interior angles are formed by two parallel lines cut by a transversal. If you look at what the different pieces of the term mean, interior is going to refer to the inside, so you're looking inside the parallel lines. And then alternate means it's going to go every other angle. So they aren't going to be right next to each other, they're going to be staggered. So examples of alternate interior angles in this diagram to the right would be angles 3 and 6. They are going to be both inside our parallel lines, and they're going to be staggered every other. Another example of alternate interior angles from this diagram would be 4 and 5. So what we are trying to prove with this theorem is that angle 3 is going to be congruent to angle 6, and that angle 4 is going to be congruent to angle 5. Now we only have to prove one of those two to be able to prove it, and then once we prove that it works for it, we're going to be able to use that a lot more in all our other theorems. One other background piece of information that we are going to need is that we are going to need to know about corresponding angles. Now corresponding angles are also formed when you have two parallel lines cut by a transversal, and what they are going to do is they're going to be angles that are going to match location from one set of the angles to the other. So if I'm looking at these as two different sets of angles, if I'm looking at this as one set of angles, and this is my second set of angles, then I'm going to have the ones that are in the same positions be corresponding angles. So for example, 1 and 5 would be corresponding, 2 and 6 would be corresponding, 3 and 7 would be corresponding, and 8 and 4 would be corresponding. Now we have a very useful postulate that we are going to be able to use. Just going back to what we talked about in class the other day, remember that when we are working with theorems, we can assume definitions and postulates. If it is a definition or if it is a postulate, we do not have to prove it to be able to use it in other proofs. We are going to give you a handy list of these. We're going to give them to you guys in class on Wednesday, but the weather had other ideas. We will get that to you the first day that we're back in class. It's going to be an interactive notebook type file that you'll be able to go back to and refer to whenever you're doing these proofs to look for different tools. Since you guys don't have that, I want to just talk about the corresponding angles postulate real quick. And what that is that if we have two parallel lines that are cut by a transversal, corresponding angles are congruent. So that is a postulate. That is something we don't have to prove. It's a mathematical fact that we're going to be able to use when we do this proof. Alright, so that should be the background information that we need. So I'm going to go ahead and get started on the proof. Alright, if you haven't done so already, go ahead and copy down the given information that you see on the screen. This is going to be the information that's provided to us to start the proof. Make sure that you have copied it down into the theorem section of your notebook. If you have not already done so, go ahead and pause the video and then come back to us and we'll get started on the proof. Alright, so by now you should have the information on the screen written down. We are going to be doing a two-column proof in this. It's going to be very similar to the vertical angle congruence theorem that we proved the other day in class. A reminder about a two-column proof. You're going to have two separate columns. On the left, you're going to give a statement, a mathematical statement. And then on the right, you're going to give a reason that allows you to justify that step mathematically. We can use definitions and postulates and theorems that we have already proven. All right, so just looking at the information we're given, we're said that we are given that L is parallel to M, and we're given a little diagram at the right to use. And we want to prove that angle 3 and angle 6 are equal to each other. So we are trying to figure out a way to prove that angle 3 and angle 6 are going to be congruent. So we have to look to see how we can get from what we were given to that step. The very first thing we're going to do with the statement, and this is going to be 99% of the time what you're doing in a proof. There are going to be some differences where you might have to start with something else, but most of the time you're going to start with something that you're given. So we were given that L is parallel to M, and our reason or justification for that is going to be that we are given that information. Now we have to take a look to see how we can justify that 3 and 6 are going to be the same. So I'm just going to do some brainstorming, and this is going to be some stuff that you guys will have to do as you get working on these proofs. The more you practice, the easier proofs are going to become for you guys. I'm going to think about all the things that I know. So far we've only used one theorem, and we've only proved that one theorem, and that was the vertical angle are congruent theorem. We did prove that, so it is fair game. So I'm just going to think about just for a minute if that's going to help us. We are starting with angle 3 and we want to get to angle 6. Now I don't have any way to directly jump to those yet, but if I'm thinking back to that vertical angle congruence theorem, that would tell me that 3 and 2 would be the same angle. So I'm going to see if that's going to help us go through this proof. I'm going to say that angle 3 and angle 2 are going to be congruent because of the vertical angles theorem. Now again, I'm going to emphasize this several times. This is a theorem that we've already proven, and that's why we're allowed to use it in this proof. If we had not proven this theorem, then we would not be able to use this. Alright? But now I have that angle 3 is congruent to angle 2, and that was by the vertical angles theorem. So now I've bridged kind of from 3 to 2. I need to see if there's a way if I can bridge the gap from 2 to 6. So I did mention a postulate when we were starting this proof, and that was the corresponding angles postulate. That tells me that if two parallel lines are cut by a transversal, corresponding angles are congruent. So if I'm looking at this, 2 and 6 are going to be, oops, moving the wrong thing again, 2 and 6 are going to be those corresponding angles. So I can say that angle 2 is congruent to angle 6 because of that corresponding angles postulate. Postulates are accepted mathematical facts, so I am perfectly allowed to use that without any hesitation. So now I have that angle 3 is congruent to angle 2, and angle 2 is going to be congruent to angle 6. And this is going to be where we're going to pull in a definition that is a property you're familiar with from algebra. If you think back to algebra when we were solving equations, we learned that if A is equal to B and B is equal to C, that A would also be equal to C. So we're going to have a very similar idea for this. And if you remember, we called that the transitive property. So because that we're saying, and I'm going to make sure I have the pen again so I'm not dragging things around, because angle 3 is congruent to angle 2, and angle 2 is congruent to angle 6, then we can say that angle 3 is going to be congruent to angle 6, which is what we were trying to get to. And our reason is the transitive property of congruence. In algebra, we called this the transitive property of equality. But since we're talking about congruence, we actually have a separate set of similar properties that we'll be talking about that refer specifically to when we're talking about congruence. But it's very similar to the transitive property of equality. And you'll notice that I stuck a little QED there at the end. This is not something that is necessarily required on the proof. What QED is a little symbol that lets us know that we have demonstrated what we sought to demonstrate. It's Latin. I had a note on there what it actually translated to in Latin, but I had to make room to add some things like the corresponding angles postulate. but that is a symbol that we can use to show that we have completed a proof. Other symbols that you might see would be a solid black square or an open black square. Talk with your teacher if they want you to use any specific symbol to indicate that we have ended a proof. All right, so there we go. That is the alternate interior angle theorem. We have now proved that if two parallel lines are cut by a transversal, then alternate interior angles are congruent. Just a couple things to tie up some loose ends. We want to always make sure that our last step is proving what we are asked to prove. It can be really nifty to prove some other things, but if you are given a specific thing that you are supposed to prove and you prove something completely different, you've kind of missed the point of that proof. All right, the other thing I want to tie up real quick, this is now a proven theorem. This is now fair game to use in future theorems that we are going to be proving. So make sure that you have all these steps copied down into your theorem section of your notebook. And that wraps up your first proof video. Go ahead down to our next video, and Ms. Blaylock is going to help you through our next proof. And I'll see you guys in another proof video down the road. All right.